after talking about these basic 5 connectives here, what we did is, so for each one of them we established some basic rules, right? Some rules that sort of define how they work. And after that, we started deriving some other rules. So the derived rules were not new things that we had to introduce. They were consequences of the basic rules, but they were useful patterns to keep in mind for the ways in which these interact with each other. Now we have seen the 4 basic rules for these two, the quantifiers. So the 4 basic rules were universal instantiation, existential instantiation, universal generalization, and existential generalization. Those are the basic rules. Those serve to define how these work. They basically give them their meaning in some sense. Now we're going to start looking at derived rules for these guys. So things that are not new, they follow from the basic rules, but they're useful patterns that tell us how these interact and how they interact with these old guys as well. So the first derived rule I want to look at has to do with the relationship between an existential quantifier followed by a universal quantifier. So an existential with a universal inside it versus a universal with an existential inside it. And in each case, the universal and the existential quantifiers are attached to the same variable. So does the order matter? Can we just switch the order? It turns out, yes, it very much does matter. So these are not equivalent. We're not going to have a double arrow like this connecting these. However, we do have an arrow going one way, and it goes this way. So this will be our first derived rule for quantifiers. And in order to prove an implication like this, we're going to have to assume this thing and then prove this thing. That means we're assuming some things that involve quantifiers, and we have to prove some things that involve quantifiers. And so we are going to have to use those 4 rules. So I am referring to these 4 rules here for using it versus proving quantified statements. And if you remember, some of these rules had some subtleties to them, like existential instantiation and universal generalization. They were quite subtle. It's not so simple to use them. Subtleties involved, the arbitrariness of the variable involved. Those kinds of subtleties are quite difficult to deal with when you just put a proposition placeholder like phi here. You really should be very clear about exactly how phi involves the variables x and y in order to make sure you use those rules correctly. And so what some people do is they will, instead of using a proposition placeholder, they'll use a proposition sort of decorated by variables to indicate what's going on, to indicate what kind of replacements have been made for those variables. Some people will do this, something like this, and maybe call these predicates. But in order to avoid all of that complication, I'm going to just replace the proposition placeholder, phi, by a very generic sounding proposition that involves both of the variables. So, or just something that involves all of the quantified variables. So if there are 3 quantified variables, then make sure that it's something generic sounding that involves 3 of them. So in this particular example, I need a proposition, a generic sounding, sort of random sounding proposition, in place of phi, which will involve x and y. And for that, I will choose y loves x. Now, usually when we're establishing a derived rule, like for example, I don't know, how about this one for how to negate an implication? This was one of our earlier derived rules, right? We're writing it using these capital Greek letters, these proposition placeholders, because we want to write something very general so that someone could come in and apply this to any situation they want and replace the capital Greek letters by any proposition they want. So the goal here, when we're not using the capital Greek letters, is to still maintain that level of generality. So think of it this way. Even though I'm using a specific sounding proposition, y loves x, that's really just to give it flavor and make it easier to think about the basic rules for quantifiers and those subtleties in there. It's still true that you can apply this to any proposition, whatever we prove, whatever derived rule we prove, namely this one, you can apply to any proposition that involves y and x. So it could be y is greater than x, or x is greater than y, or the point x comma y in the plane has a distance of 7 from some other point, something like that. Any statement involving x and y can go in place of this, y loves x. So I also just want to show you the format when you're looking over these in the notes. What I'll do is a very generic format, like this, where I use the capital Greek letters so that you really can just replace the capital Greek letters by anything you want, and that would be a valid application of the derived rule. But I also show you what I'm referring to as a particular instance, which is the derived rule but with this generic sounding proposition in here. Now, what I would recommend when you read these on your own is skip this part first. Maybe read the statement, but skip this version of the proof. Instead, read this version of the proof. Make sure this version makes sense to you. Then, if you want to, optionally, go back and look at this version, which will be the same but with Greek letters in different places. Then you can make sure that that also makes sense. So, just prioritize reading this, since this is... Prioritize reading that second part, the part with the random proposition filled in, because this is what will probably touch your intuition more closely. And part of our goal is to make the logical arguments that are, logically valid and using all of the rules formally intuitive also. That is a major goal.